Okay, so we will first find the domain. Can we accept every x and every y? Well, y is okay, but x has some problems, right? You want to avoid x being equal to 0, x squared being equal to 0, but that's the same thing as x is equal to 0. All right, so what is a domain? Don't write x is equal to 0 because that's exactly the opposite of the domain, right? So the domain should be all of xy such that x is not equal to 0. Okay, you can say all of the plane r square except the line x is equal to 0. That would be acceptable. Okay, if you say except x is equal to 0, because those are the points that you're trying to avoid. X. So in other words, every point here on the y-axis, that's where x is equal to 0. Okay, so those points are to be avoided. Those points are not on the in the domain. And in fact, x is equal to 0. This is the boundary for the domain. Now, why is it? Because if you pick every point on the y-axis, okay, and draw any kind of a neighborhood or an epsilon ball or any open set, basically any open set including this point, containing this point, okay, includes a point or many points outside of this domain, and all those points are inside of the domain, right? Because every point off of the y-axis is in the domain. So every one of these epsilon balls about a point, any point on the y-axis contains both points on the domain and points outside of the domain. So the boundary for this domain is that entire line, y is equal to 0, x is equal to 0, otherwise known as the y-axis. So the y-axis is the boundary for this domain. Okay, how about the range? Well, the range is, so if let's restrict x equals 1. Okay, so then if you say, because 1 is okay to have this, right? So if x is restricted to 1, right? F of xy is f of xy is simply y, right? And of course, y can be anything from negative to positive infinity. And so even when you restrict x to 1, you have the range from negative infinity to positive infinity. So regardless of what x is, of course, x can be 0, but if x is 4,000, you still can, range the value from negative to positive infinity. So the answer to the range is that it is from negative to positive infinity, or you can just say the entire real numbers. You can just write this script R, and that would be the answer to the range. Okay, few level curves. So if you say y over x squared is k, clearly y is k x squared. Remember, x is not 0, right? So if x is 1, for instance, you get this curve, right? Oh, yeah, so if you can't have x 0, so you may want to have a hole here, okay? In fact, you have to have some sort of an indication that x cannot be equal to 0. So it'll be like the parabola. In fact, it is a parabola, except you have the hole right in the middle. If x is 0, then what happens? Yeah, if x is 0, you just get the straight line except for the origin. So if k is 0, then your level curve will be a straight line except for the hole. If it's negative, if x is negative 1, for instance, then you have this, right? If k is 2, then you have 2x squared, which is a little thinner, parabola. Okay, but all of these have that missing point, which is the origin. So those are the level curves. Okay, so you can say the level curve. So level curves. If you have to describe level curves in your own language, in English, then you would say the level curves. We use a nice word, a family, family of parabolas. And it's okay to say a family of parabolas, even though one of them is a line minus a point, because that's a degenerate case. Okay, it's a family of parabolas, except 0, 0. You want to make sure that these parabolas do not include the origin. Okay. you can say a family of parabolas with holes, a hole if you like. All right, so just the last item I should mention before I do this one example is this. Maybe no, you know what, let me just do an example first. Okay, so here's another example, and I want to describe or illustrate this idea called traces using this particular example. Okay, you can see the domain here is the set of all r's, all points x, y, so that x is not -1, right? Okay, so something happens at -1 when x is -1, f is undefined. It goes to infinity from one side and -infinity from the other side. This is a typical function. All right, and so what is a trace? Okay, traces are very closely related to the level curves. Remember, for level curves, you let z be equal to a constant. Okay, traces are the cross sections. Sounds familiar, right? Cross sections where x or y is constant. So again, it's not a big deal, right? So let's see. If x is equal to 1 in this case, then f of xy, of course, you can write this as f of 1y. And so what that means is that you get 2i over 1 plus 1, which is simply 2y over y, which is y, right? So then the trace when x is 1 is actually x is 1, so there is no x coordinate. When you cross this the graph of this surface where x is equal to 1, the vertical wall, you know, where x is equal to 1, then the cross section, the trace when x is 1 is going to look exactly like this. Z is equal to y. Okay, so that's what it is. If x is equal to 9, though, it's going to look very different. And I'm just choosing, you know, some random numbers for x. 9 is a good number. 2y over 9 plus 1, 10, right? So this will be 1/5 times y. So here, the graph is going to be of a smaller slope, okay? And so this will be your trace where x is equal to 9. So this is not a hard concept, all right? So you know, basically it's just a cross section to see what happens if you cross or if you cut the surface at a particular x value or y value. Okay, so finally, let me explain one more thing. A level blank, we've been talking about level curves, but what happens if you have f, a function of 3 variables? Okay, so in this case, what happens is, you know, here's an example. Let's say f, x, y, z is x squared plus y squared plus z squared. That's an easy one. All right, so what happens then if, for instance, if f is 1? Okay, well, obviously, this is just a sphere of radius 1, right? Okay, so that's going to be just a, you know, a sphere, unit sphere. Okay, how about if f, you know, here, this whole thing is 2. So if you want to call this, remember w, okay, if w, the level blank for w is equal to 1 is the unit sphere. If you want w to be equal to 4, then this is what you get. And that's a sphere of radius 2, which is like this, okay? So what you get is not level curves, but level surfaces. So when you have functions of 3 variables, x, y, and z, then you don't talk about level curves, but you have to talk about level surfaces. And this is primarily the way we visualize functions of 3 variables. Remember, if you have functions of 2 variables, you can actually graph the function, you know, sort of like what I had here. And then you can here, if you want to do you know, if you want to draw these level surfaces right on the surface, it will look like this, right? And you can clearly see these things. Well, if you have 3 variables, like I said at the beginning, you cannot graph the function because that would require a 4th dimension, which is very hard to imagine. And if you can imagine that fourth dimension, please let me know. We will write a book together. But normally we just can't do that. But we can draw level surfaces, okay? And that's a way for us to primarily understand this. By the way, what does this look like? I mean, typically, it'll be not a nice function like this. What happens if f of x, here's just another example. What happens if f of x, y, z is, 2xy plus y square over z minus sine of x plus z or something, right? So what this means is at every point x, y, z, there's a unique number associated with that number, with that point, which is f of x, y, z. That would be the value of this function, right? And so you can clearly see some application of this, right? So this may be f of x, y, z may be describing what? Some real number associated with the point x, y, z. So for instance, a function of 3 variables can be expressing the temperature at the point x, y, z, okay? How about like the air pressure at the point x, y, z? How about, some density at x, y, z? So these are very important things, so functions of 3 variables can be very applicable, can be applied or can be used in many application problems. It's hard to graph these. But in that case, what you can do is to connect all the points of the same temperature, and they may look like this, right? That would be the level surface, otherwise known as the isothermal surfaces. Okay, isothermal sets, which means the set of all points with the same temperature, or with all the same points with the same pressure and so on. So these are, and they can be very, very convenient in application problems. Okay, so that's pretty much all I'm going to say about section 4.1. In section 4.2, we'll be looking at limits and continuity of these functions. And there's one very tricky thing about limits. And so that's what we'll be studying. All right, so until we see you in section 4.2, I hope you will have a great day and a great week. Take care.